So welcome. My name is Jennifer Griffith, and I work at NUMOA, which is the Northeast Waste Management Officials Association. For those of you that don't know what NUMOA is, we're an interstate association of the 6 New England states, New York, and New Jersey. We focus on waste issues, so that's solid waste and hazardous waste, pollution prevention, toxics in products, but also the waste site cleanup programs, and that's mainly who I work for at NUMOA. The waste site cleanup programs priority is training and information sharing, and that's what we're doing today. PFAS has been a high priority in the NUMOA region since about 2016. I think we had our first meeting and webinars on that. So we are continuing that tradition today with some information sharing on the webinar today. So the purpose of the webinar is, like I said, to share information and prompt discussion. So please don't take this as an endorsement by NUMOA or the NUMOA member states of the presenters or the perspective those presenters are going to present today. We will be posting presentations after the webinar on the NUMOA website, so that's part of why I've got it open here. Dave, are you seeing the NUMOA website?
I am.
Great. So NUMOA's website is very old, so it doesn't scale to your screen, unfortunately, but it's very functional, and so this just gives people an idea of what NUMOA is. But then afterwards, we will be posting the presentations. I will send an email out to everybody that attended today with the link. But you can find the information. You go over here to the left-hand nav. There's a waste site cleanup button. Click on that, and then you get to this screen where there's an events. So you click on events, and this is everything upcoming. We have a bunch more webinars in case you're not aware about PFAS. The furthest thing out in the future is at the top, and then things that are closer, you have to scroll down. So here we are today. We've got perspectives on a class approach to PFAS, and then below upcoming events is the past events. So you can, here it is again, because it's also going to be in the past in just a few minutes. The presentations will be posted, and presentations from prior webinars are also accessible here, as well as NUMOA in the past has held several workshops, and the presentations from workshops are also posted. We have webinars and training on topics that are not all PFAS, but other waste site cleanup topics. So there's a lot of information here, and I encourage people to visit the NUMOA website in the future. So with that, there are quite a few people on the webinar today, which is great. We've got people from states all across the country and government agencies from local to the federal, and then some consultants and some nonprofits, a good mix of people. But there's way too many people for people to be able to ask their questions live. So I will be monitoring questions. You should use the question box in your GoToMeeting or GoToWebinar control panel. There's a question section, so you can type in your questions at any point. You don't have to wait until the presentation is over to type in questions. So you can ask a question at any point. I'll be monitoring those, and we'll ask the questions after each presenter presents today. So we are very fortunate to have two excellent and fascinating presenters. We've got Dave Andrews from the Environmental Working Group, and then Simona Balin, who is with the California Department of Toxic Substances Control. So the first presenter is going to be David Andrews. He's a senior scientist. Let me just give him the controls here. At the Environmental Working Group, where he uses his background in chemistry to investigate public and environmental health issues. His work focuses on finding ways to protect public health by educating consumers and changing national regulations and government policies. He has used his knowledge of industrial chemicals, consumer products, and nanomaterials to work on consumer-facing databases and to communicate with government agencies. He holds a Bachelor of Arts in Chemistry from Wesleyan University and a PhD in Chemistry from Northwestern. And Dave, I think I gave you the controls, but we are not seeing your screen.
1 second here. Let me, I apologize. Oh, here we go.
Okay, we're seeing them. Oh, there you are. Perfect. So with that, so David will present and people can type in questions at any point, and then I will ask questions for a few minutes after his presentation. So with that, take it away, Dave.
Thank you. And thank you for the introduction. My name is David Andrews. I'm a senior scientist at Environmental Working Group. I've been with the organization for over a decade now, working on really trying to understand the implications of industrial chemicals, chemicals in consumer products, and their impacts on health. It's previously at Northwestern where I worked on my PhD and much more fundamental chemistry, chemical physics, and some of the research I did at the time was looking at, and I was in a lab that was doing some work on carbon nanotubes. And this was around the time that there's initial national health stories about the potential asbestos-like behavior of carbon nanotubes. And I realized that I had given, up until that point, very little consideration of environmental health and public health impacts of these chemicals that we were either developing, proposing, or considering in a chemistry context. And so I made the switch to working at Environmental Working Group after that. So start off with an internet meme in terms of how it started. This is an image from ACS CNE News on just showing PFOA and PFAS and their chemical structures. How it's going, you know, these are forever chemicals. It seems decades later, these are the chemicals with the most prominence in public health attention. They continue to be the ones with the most prominence in public health attention. They have not yet, or they have not been effectively banned in commerce. There's a voluntary phase out from the major manufacturers. These are the chemicals we are still discussing and are still being researched in significant detail. And at the same time, how it's going also includes, I went to the EPA ChemView website and pulled out at least the first few dozen of other PFAS compounds that are being used, manufactured, made, ones that we know much less about other than the fact that they've been approved for commercial use. So really the complexity of this PFAS problem has only expanded, and yet from a regulatory and even toxicity perspective, we are still significantly focused on PFOA and PFAS. First, a little bit of, here's an outline, a little bit of introduction on Environmental Working Group. We were founded in 1993. We're a nonprofit, nonpartisan organization. And our primary mission is to empower people to live healthier lives in a healthy environment. We are focused on public education, making this information easily accessible on the internet. One of our big focuses is really making large and often government data sets available online. And this is everything from farm subsidy information to drinking water test results from utilities around the country, where we collect it at the state level and compile what is essentially a national database of drinking water test results. And that you can actually look up approximately the last 5 years of test results, providing much more detail than even found in consumer confidence reports. We also have databases of cosmetic products, cleaning products, the ingredients in there, and actually packaged food products also. And we have for consumers and available on both Apple and Android is an app that compiles all of this information, both our product evaluations in terms of the ingredients in those products, as well as some of our drinking water information. But in terms of PFAS chemicals, we have done a significant number of reports, original analysis, testing of off-gassing, testing of drinking water occurrence, and maps, really an incredible array of different resources available online. Here, I'm just pointing out 2 timelines that we put together in terms of what DuPont, 3M, and some of the original manufacturers knew about these compounds when. And you can find some of these original documents online on our website, where we link to the PDFs, and also what was known by the Department of Defense about the concerns about the AFFF and firefighting foam. And actually, we originally got our start on PFAS with the release of the discovery documents in DuPont. And this is by Rob Bilott. People are likely aware from the movie Dark Waters. It's the release of the release of those files through discovery. And we actually made the whole docket available online, available to the public, available to reporters. This was a database that just held all of those documents and made them really accessible. Some of those documents included cord blood sampling of women and infants or embryos. And some of those results, like this one here, actually, that information had not been previously submitted to EPA. We filed a petition along with Rob Bilott that ended up leading to a fine of DuPont for failure to disclose this information within 8E filings. And so really, the lack of transparency in terms of the toxicity of these compounds is something that we've seen repeatedly. We've done a number of different reports in this space. We had public letters to the CDC in 2002 asking for biomonitoring of the American public for the occurrence of these compounds. Studies really trying to understand the scope of this contamination. I'm highlighting another report here from 2009, where we looked at PFOA concentration in DC tap water. Interesting to note that a decade later, we released a report just about a year ago now. The levels are relatively similar at 3 to 3.5 parts per trillion. And then here's another report we put out in 2015. And as I said, we've got a significant number of reports on our website. But I'm going to talk about where consumers and where the public are exposed to PFAS, and where their introduction comes to PFAS. And we often think of Teflon nonstick pans, but in most of the risk assessments to date, food is and diet is considered to be a major, if not the major, source of PFAS exposure. And so actually, when we discovered that PFAS were used in food packaging materials back in 2003, we wrote letters, the organization did, to 9 fast food chains. And we actually, in those letters, explicitly said, if you're using fluorinated chemicals in food packaging, we look forward to hearing your plans to move away from that. At that time, and somewhat based on the information coming out about PFOA, companies shifted to not fluorine-free packaging, but PFOA-free packaging. So there was a slight shift, but one that didn't move away from this class of compounds. Likewise, we in 2008, 2009, we analyzed in depth the alternatives and what information was publicly available. And really, there's a significant lack of disclosure in terms of which compounds were being used and what was leaching out of food packaging. And this is of particular interest because of how common these materials were. And so we found out how common in this 2017 paper. That was actually, Simona was one of my co-authors on that paper, where we were looking at fast food wrappers and food sandwich wrappers collected from really fast food chains and the biggest fast food chains across the country. We collected approximately 500 samples. We found that 40 to 50% of these different product categories had added PFAS to them. But like most papers, I think a lot of the interesting information, I mean, this is an interesting look at the marketplace in general and what's in these food wrappers. But a lot of the interesting information is in the supporting information. And here, this image or this graph shows some of the results from liquid chromatography time of flight mass spec. This is done by EPA researchers who were collaborators on this project, and identification of 27 known PFAS compounds. And these are the ones that they could, at the time, identify in the sample. And what we find is incredible diversity in these PFAS compounds in terms of perfluorocarboxylic acids, perfluorosulfonic acids, fluorotelmer sulfonates, dipaps, perfluoroethers. And you see across these samples just how the amazing diversity in the number of compounds. I will say 6 out of 20 of these samples had detectable PFOA. A similar number had PFHXA, PFBS. A few also had Gen X, Adona as detectable PFAS in them. And then also in the supporting information is a plot of the unknown PFAS in those samples. And for some of these products, it made up a majority. And this unknown PFAS was identified just through CF2 mass differences. So this is looking for a characteristic of the CF2 group as part of the molecule. So even that may not be comprehensive in terms of the different PFAS compounds being used in these fast food wrappers. But what this is highlighting is that for the public and for people are just not being exposed to 1 or 2 PFAS. They are being exposed to a significant number of PFAS. And so if we're focusing our studies on toxicity on 1 or 2 compounds, what are we saying about the rest of them, if anything? To that point, a quick look at PFAS in water, I think also further illustrates really the diversity of PFAS that people are being exposed to. And so this is, these papers are really interesting. This is by Donald Tavies, who did some original work in the 60s, looking at blood samples. He was originally looked at his blood samples, I believe, and was doing work to identify and correlate the levels of fluorine in blood with fluorination of public water supplies, and not finding a correlation. And digging into this, discovered that it's the lack of a correlation was due to the presence of organic fluorine in samples. And so within I think it took about 8 years before the statement at the top of the slide was published that his findings were suggesting really widespread contamination of human tissue with trace amounts of organic fluorine fluorocompounds derived from commercial products. And so this was not focused on a single compound, but really looking at organic fluorine in blood. And so it's an interesting reminder of that's how we actually discovered that PFAS were so widespread, was because of testing for organic fluorine, not specific to PFOA or PFAS or a single compound. In 2015, we actually started mapping the PFAS occurrence in drinking water supplies across the United States. These were using the results from EPA's Unregulated Contaminant Monitoring Program. This program only tested for 6 PFAS compounds, including PFOA and PFAS, as well as PFBS, PFNA, PFHXA, and PFHPA. And it had relatively high detection limits. The other limitation of this program is that it's only testing water supplies that serve over 10,000 people. There's a small sampling of smaller systems, but really this is focused on the largest public water supplies in the United States. Subsequently, I worked with colleagues on really trying to identify sources of this PFAS in the drinking water and really correlating these positive detects in the nationwide sampling with industrial manufacturing, firefighting, training sites, and wastewater treatment plants. But this opens up an interesting question in terms of what is missed when you're looking at just PFOA and PFAS. And thanks to this study and a number of studies by these co-authors, in particular Mark Schreiner and Andrew Lindstrom at EPA, who've done papers, both this paper is focused on the Cape Fear River Basin in North Carolina, but as well as newer studies in New Jersey and Alabama, looking downstream of manufacturing facilities and actually characterizing what's in the water supply. We're really starting to understand the scope and the magnitude of this PFAS class of compounds that may be occurring in drinking water. And so this is interesting. They're characterizing the red bar is characterizing the high levels of Gen X in the drinking water supply downstream from the Chemours manufacturing facility. And on this slide, it shows that higher level value of Gen X along with PFOA, PFAS, and some of the other often characterized PFAS contaminants. And what is really striking is when you look at the plot on the right is how small of a portion those compounds make, and those, this is in the hundreds of parts per trillion, make in comparison to the other fluorinated compounds that are occurring in the drinking water supply there, which are orders of magnitude higher concentration, which really opens up a lot of questions in terms of what other organic fluorine compounds are out there, and what other potential impacts can they be having, or may they be having, on public health. And so that's the lens that we are looking at this issue of, and the lens that's being presented to the public. Subsequently, and this is an online interactive map, we've been and continue to update a nationwide map that includes drinking water testing from water supplies. The states with the highest concentration of dots are states that have tested a significant portion of their water systems. It's largely a function of how many water systems have been tested and what was their detection limit on whether or not they're shown on this map. And to date, we've got over 2,300 sites on here. And we also have highlighted the military sites. Many of those are due to AFFF contamination and our groundwater samples. But I want to highlight this paper also. This is a paper that came out of EPA and USGS researchers looking at PFAS substances in source and treated drinking water in the United States. They looked at 25 water systems. And what they found, they had the sum total concentration of PFOA and PFAS was approximately, or just under 6 parts per trillion in the source water, slightly lower at 4 parts per trillion in the treated drinking water. For other contaminants, those concentrations were even closer. But one thing that stood out was the total concentration of the, I believe it was 17 PFAS compounds that they're testing for, was closer to 20 parts per trillion in the source and treated drinking water. And the question is, what's the impact of that cumulative exposure? Most of the focus and most of the discussion on setting a national drinking water standard and EPA's efforts have been directed at PFOA and PFAS. And yet we know, at least even with an expanded set of tests, that the total organic fluorine concentrations in water and PFAS concentrations are at least a factor of 4 or 5 higher. Likewise, this is the paper that I worked on in the last year, just looking at the percentage of population served, and these are community water system tests. As a function of concentration, what percentage of the population is likely exposed? And so this shows that as you go to lower some PFOA and PFAS concentrations, a high percentage of the population and a high percentage of the water systems have those detections. The majority of larger public water systems are surface water fed. And what we found is that at lower parts per trillion concentration, these contaminants were nearly ubiquitous in public water supplies. And actually testing that EWG published just over a year ago, where we looked at 44 drinking water systems in 31 states in Washington, D.C. Every single one of them except one had a PFAS detect. But of particular interest, and I wish I could have gone farther in terms of doing a sum concentration for all known PFAS or a total organic fluorine concentration, that wasn't possible with the data that's currently available. And so, but what we did note is that that when you looked at the sum concentration of tested PFAS, it was approximately a factor of 10 higher. And so we saw 51% of the water systems we tested, as well as the EPA testing of larger systems, had a total PFAS concentration over 10 parts per trillion, or nanograms per liter. And so this is a further study I'd like to highlight that looked at 5 cities in Massachusetts, and actually looked at water sample tests from 2016 in comparison to 1990. And what they found is that the unknown component has increased significantly in the last 2.5 decades in terms of PFAS compounds in the drinking water. There's some change in PFOA and PFAS and other identifiable PFAS, but it really the unknown concentration stands out as something that has significantly increased over time. And what those are, to be determined, but I think this highlights really the scope of the problem and why just focusing on PFOA and PFAS is likely minimizing the potential problem. So I want to highlight also some of the health concerns from a public perspective. And so EWG started doing testing of umbilical cord blood a decade and a half, 2 decades ago. And one of the first compounds we tested for were PFAS compounds that are found in nearly all samples, just like sampling of human blood by the Center for Disease Control. What we know, and at least in terms of human epidemiological evidence, is largely from Parkersburg, West Virginia, and the unique settlement agreement in terms of medical monitoring and blood testing of nearly 70,000 residents in and around Parkersburg, West Virginia. And this led to the probable link reports. Those are all available online. But linking exposure to PFOA to high cholesterol, testicular kidney cancer, thyroid disease, ulcerative colitis, and pregnancy-induced hypertension. But the question in terms of regulating and considering PFAS as a class are, what about the other compounds that are out there? What do we know? And what can we do with that? And so this is a table that we compiled with information from ATSDR, NTP, EPA, as well as some of the peer-reviewed literature. This is available on our website, but just highlights how, at least of the compounds that have been studied to date, there's significant overlap in terms of the impacts or potential impacts to a significant number of bodily systems, and really highlighting how the potential for harm has not seemingly gone away from this essentially second generation of PFAS compounds. And to that point, on the health effects, I just wanted to highlight on the top is the FDA phase-out agreement for PFAS use in food packaging materials. This is in reference to the 6,2-fluorotellumer alcohols. These are also commonly used in carpets and upholstery. And these are very relevant because the industry focus and a lot of the defense of these 6,2-fluorotellumer alcohols were toxicity studies done on PFHXA, which is one of the primary breakdown products. But this phase-out agreement is due to concerns that the FDA raised about how when you study the 6,2-fluorotellumer alcohol and not the predominant breakdown product, you end up with other compounds such as the 5,3 acid, which actually do seem to bioaccumulate to a greater extent. And when you start with the 6,2-fluorotellumer alcohol, you see evidence of much greater toxicity than if you look at just one of the breakdown products. And this slide really stands out in highlighting the complexity of PFAS exposure and where the toxicity may be coming from may not be the predominant breakdown product. And that's significantly relevant in terms of a regulatory context and proving safety. And then at the bottom, I'm highlighting one of the perfluoroether compounds that was used as a replacement for PFNA. And this stands out in terms of the incredible array of health effects documented in workers who are exposed to this compound. And this is biomonitoring of workers and looking at associated health effects in terms of potential impact on the body. And so now it's in that frame that we're looking at PFAS as a class. And so in 2019, I wrote a piece that has a corresponding counterpart by someone from the Fluorochemistry Council, highlighting why, from a public health perspective, we should look at PFAS as a class. And I think the place this really starts is our point of view that the system is broken. We've gotten to a place where there are 600 to 1,000 PFAS chemicals, maybe more, that have been used industrially in the United States over the last few decades. Everyone is exposed to mixtures of these compounds. The evidence we currently have is that they have shared health concerns, and ultimately the presumption of safety is really no longer valid. And then the counterpoint argument here is that our current system works just fine. There's lots of different PFAS, they have different health effects, they're all unique, and everyone's exposed to chemicals, so it's not an issue. And I think that's kind of where this comes to a head in terms of highlighting that ultimately it seems the system is broken. And so this was a publication that came out last year with a significant number of collaborators looking at the scientific basis for managing PFAS as a class. It follows some of that similar structure in the Bloomberg piece. But I want to highlight that this is really trying to also encompass all PFAS. So this is the perfluoroalkyl acids. So this is your PFOA, your PFAS. The precursors to those, so that those are compounds with side chain polymers that may transform into PFOA or PFAS, so they transform into other stable and persistent compounds. This is the shorter chain replacement for those. In gray here are the fluoropolymers and the perfluoroethers. And actually we have a reference in this paper highlighting how, by one estimate, it's actually the production of the fluoropolymers that are the source of over 80% of the perfluorocarboxylic acid contaminants in the environment. So highlighting how the production and the entire life cycle analysis of these fluoropolymers is what has led to the significant portion of the contamination that's out there to date. And also we highlight that the shorter chain PFAS, they're equally persistent. They're more difficult to remove from drinking water, groundwater. Some of them have bioaccumulation properties, and they often have greater uptake into plants. So the question is PFAS risk management, and highlighting that the system isn't broken. And the big concern here is that our current regulatory approach is going for extreme accuracy and precision for just a few compounds. But this is being done at the expense of accuracy for the majority of PFAS compounds in use. And so this approach is systematically ignoring what is the majority of PFAS compounds by focusing on just a few. So to approach that, there are numerous state regulations that are now shifting in a different direction in terms of evaluating use categories for the entire family of compounds. And that's looking at food contact materials, packaging materials, firefighting foam. And there's also at least on the regulatory side, this question of how you treat treatment, disposal, cleanup standards, and combined human exposure. And from the evidence here, our perspective is that if you just focus on PFOA and PFAS, what are you saying about the other compounds that are occurring in drinking water? And ultimately, the need is to make this category as broad as possible because of the evidence that's available. And then in terms of marketplace, this is highlighting how at least many users and companies have started shifting towards a class-based approach to PFAS compounds. And I don't know if everyone has seen this week the announcement by Keen, the shoe manufacturer, that has highlighted their road to going PFAS free and really putting that blueprint out there for other companies to follow and calling on the industry to move to PFAS free. Also other companies and brands such as IKEA, Levi's, Crate & Barrel, who have made public announcements to move away from this entire class of concerning chemistry. And then on the essential use end, this is really highlighting a different perspective in terms of, are these compounds necessary for the health and safety or critical functioning of society? And calling into question the widespread use of concerning chemicals, concerning persistent chemicals that may be building up in the environment and building up in bodies before approving them for use, or when there is concerning evidence, those are the places that, non-essential uses are the places that we should end the use of these compounds as soon as possible, especially in the absence of data showing otherwise. And as I mentioned earlier, really this presumption of safety that exists for industrial chemicals should no longer apply to this chemical class of concern. And so in summary, this is really the high-level takeaway is for this recent publication on managing PFAS as a chemical class is that these compounds are extremely persistent and show potential for harm. And we really need a more efficient approach to address the thousands of PFAS compounds that have industrial use or may be occurring as evidence of byproducts, manufacturing impurities, or transformation products that occur in the environment. The most consistent feature is the persistence, which leads to the accumulation in people, water, sediment, soil, and living organisms, high mobility, and really the broad range of adverse health outcomes associated with exposure is of significant concern, and that exists for many of these replacement compounds, at least the ones we have evidence. And so with that, that's my summary, and I'll turn it back to Jennifer. Thank you.
Great. Well, thank you so much, David. We do have some questions that have come in, and I'm sure people will be typing now. You might not want to totally go away. Yeah. So people are wondering about how is total organic fluorine measured? Is it a common analytical test?
Yeah, that's a great question, and honestly, one of the difficulties in this space in terms of a class approach. There are some methods that are available for measuring total fluorine. In our fast food wrapper paper, we used the PIGGY method, which is a gamma ray based method, but it's not differentiating between organic and inorganic fluorine. There's also a method for doing inoxidizable precursors and then testing, and then there's methods for doing flame ionization, but to date there is not a standardized approved testing methodology for total fluorine, and that is an urgent need in terms of both addressing this contamination as well as moving forward in terms of addressing them as a class.
Okay. And then somebody was interested in, and I think this is good background. What drove the inquiry into into organic fluorine in the blood? Like, how did
I
this
believe
even
that
come
was,
about?
yeah. So in that paper, the papers I mentioned from Dr. Tavies, he was looking at fluorine levels in the blood to see if it correlated with fluoridation of public drinking water. And so it was the lack of that correlation that led down the path of trying to determine why there was no correlation between water fluorination and fluoride levels in blood.
So people were concerned maybe that adding fluorine to drinking water wasn't a good idea, so someone was trying to look into that. That's kind of where it
I don't know
started?
whether or not they were addressing the issue of whether it was a concern or not, but looking at the correlation between the fluorination of water and the fluorine in blood.
Okay. Of the 29 PFAS EPA has proposed to be monitored in its next round of UCMR drinking water supply testing, how many are the newer forms of the PFAS, the ones that are, like, are they the most commonly used ones, and how many of them are the newer forms rather than the old?
That's a great question. I don't know offhand what the exact breakdown is. I want to say on order of half are some of the longer chain and half for some of the shorter chain replacement chemicals, but I don't know exactly offhand. But on that order, and I know a number of some of the more common processing aids and shorter chain breakdown products are represented in that testing.
Okay, let's see here. What is the basis for the evidence for cancer for most of the PFAS that you had listed in the table of health endpoints?
So in terms of, and I'd be happy to refer back to, let me see what slide that was, to pull that up again and the reference therein, but and happy to reference to our website here. A number of, well, and it's also worth noting that I believe it's this past week that OEHA in California proposed listing PFOA as a known carcinogen. I don't have the references to go through all of these here in terms of the documented evidence with respect to cancer, but we did highlight at least the ones with the strongest evidence were PFOA, PFAS, and Gen X.
Okay. Here's a general question, then I've got one more. But is there any evidence correlating the size of the PFAS molecules with the health effect? Like bigger have worse health effects and smaller have less worse, or is there any generalization there?
Yeah, no, that's an interesting question, and a lot of and actually NTP has really tried to take on this question in a number of the studies they've done in terms of normalizing internal dose to the compounds. And I believe with a normalized internal dose, many of the shorter chain compounds show greater toxicity. The difference is that those have shorter half-lives in the body, so they're excreted more quickly. So if you're exposed to the same quantities of them, the shorter compounds may show lower toxicity, but in terms of a normalized internal dose, I believe a number of the shorter compounds have actually shown increased toxicity.
Okay, and then one question that a lot of folks on this webinar have is just the class approach seems to make a lot of sense for future use and use in products, but from the cleanup and the remediation perspective, do you have some thoughts about how you would, given that different compounds have different health effects and environmental effects, how you would be able to group things together in a sort of looking at the contamination that's already out there?
Right, and this is this class approach definitely is a significant change from the current framework, and it not necessarily easy to implement in every situation. In terms of the cleanup and looking at treatment disposal of PFAS compounds, I think that the important piece is measuring as broadly as possible for these compounds, and ultimately what we want to avoid is treatment technology that addresses PFOA and PFAS, but for example ignores PFHXS, another long chain compound that's found with some regularity, especially in places that used firefighting foam. I think that's a really important question that kind of gets to the heart of the matter in terms of addressing these compounds. But from the public perspective, we think that cleanup standards should be as broad as possible because of the potential cumulative effect of exposure to these compounds. But definitely something that needs to be developed more.
Right, because we don't have the good toxicology studies on a lot of these compounds, but if we could identify more of them that seem to be, coming up more commonly, then that might push some studies.
Well, and the concern here is that we will never have complete toxicity data sets for all of these compounds. And that's really the crux of the matter, and why this shift towards this class approach is that it's taken what is now 3 or 5 decades to accumulate the evidence of PFOA and PFAS harm and directly harm to human health, and to the point where we have not even yet set a national drinking water standard for those compounds. And so with 1,000 PFAS compounds that have been commercially used and thousands more that may be detectable in the environment or in products, the current approach is not working.
Mm-hmm. Okay, well, I think there are some more questions that have come in. Unfortunately, I think we're going to need to move on, though, so maybe we can get to some of them at the end. Some of them are related to David, if you would be willing to present to other folks in other places. So I will connect with David about that and relay those to him. And also maybe for when we are towards the end of our time today, David, it looks like some folks would like to know where they can find some of the maps and some of the things that you showed. So maybe towards the end, close to the 3 o'clock time, I can put you back on and you can show folks the website for EWG and where some things are. So
EWG.org, and all of those resources are there.
And there's like a PFAS button that people can find easily or something.
Yes.
Okay. Well, also at the end, I can, have you show your screen again too. So, all right. With that, I think we're going to move on now for our second presenter. So David gave sort of a more of a background and making a case, and then Simona Bailan is going to present more about what a particular state is doing and their work. So she is a senior environmental scientist at California's Department of Toxic Substances Control, which is also DTSC, where she leads the Safer Consumer Products team working on PFAS. Before joining DTSC, she was a senior scientist at the Green Science Policy Institute, managing international projects on the use of flame retardants and PFAS in consumer products. She has a PhD in environmental science, policy, and management from University of California, Berkeley, and a Bachelor of Science in Earth and Planetary Sciences from Jacobs University in Bremen, Germany. So with that, take it away, Simona.
Thank you, Jennifer. And just to make sure you can see my presentation slides right now.
Yes, I can. Thank you.
Awesome. All right, so thank you for the invitation to speak here, and thank you for David for doing that introductory talk, because it really set the basis for what I'm going to cover today. So hopefully there's not going to be too much overlap. I basically want to show you how this idea of regulating chemicals, or PFAS in particular, as a class is not only doable, but it is being done. And at the California Department of Toxic Substances Control in the Safer Consumer Products program, we believe that this really is the only meaningful way to regulate these chemicals as a class, and that trying to regulate them individually would not make sense from a regulatory point of view. So I will explain to you today how our regulations work. Because they are unique, they do have some features that are unique to these regulations. But as you'll see, some of these concepts and principles that we're using can be applied to other regulatory programs, and that's what we hope that others will be able to use this approach as well. So without further ado, this is the framework of the Safer Consumer Products program. It's a four-part framework. It starts with the candidate chemicals list that basically pulls from 23 authoritative lists. And it has thousands of compounds in there, including the entire class of PFASs. And basically the work that we do in SCP, in the Safer Consumer Products program, is to identify consumer products that contain one or more of those candidate chemicals. And once we prioritize those product chemical combinations, we call them priority products, and we add them to the California Code of Regulation through a formal rulemaking process. And once that rulemaking is finalized, then manufacturers who use that candidate chemical in their product, who basically want to sell that priority product in California, they have a few options. They could take the product off the market, they could replace the chemical, or they could go through an alternatives analysis process where they evaluate the available alternatives, and we review their analysis, and based on that we take a regulatory response, which can have a wide range of possible actions on a case-by-case basis. So it's a pretty complex process. It's not like a legislative ban for a chemical, because it is designed to ensure that regrettable substitutions are avoided, that these replacements are not worse or just as bad as the chemical that they're replacing. So it's a thoughtful evaluation of alternatives to make that case. So let's start from the beginning. Our menu of options, as I mentioned, is pulled from 23 authoritative lists, and that includes a wide range of compounds that are on this list, maybe because they are carcinogens, mutagens, or reproductive toxicants, or persistent bioaccumulative and toxic, or respiratory toxicants, and so on. And some of these lists are what we call hazard-based lists. They list chemicals with known toxicity or known PBT properties. But some of those lists are what we call exposure lists, because they include chemicals that have been found in humans or in the environment and are of concern because of their presence in either in the population or in the environment. So one of those lists is the list of priority chemicals for biomonitoring in California, for instance. However, we do not tackle pesticides or dangerous drugs or radioactive chemicals or natural toxins. So if those are included on those lists, we remove them from the scope of our work. So PFASs are on our list because they were added back in 2015 by Biomonitoring California to their list of priority chemicals. And they added the entire class as defined by Buck et al. 2011. That was the very first paper that introduced the terminology of PFASs. And by the way, you may notice that I call them PFASs, unlike a lot of people who call them PFAS. That was the original terminology of Buck et al., and they did have that extra S at the end. And I personally think it makes sense because, there's PCBs and PAHs and PBDs and so on. And it drives the point home that this is a class of chemicals. I know that, some think that PFAS is already plural, that it's per and polyfluoroalkyl substances. But I think it's more like per or polyfluoroalkyl substances. And that is important from a regulatory perspective as well, because, one chemical, it could be that there's, perfluorinated chemicals in a consumer product or in a media, or maybe there's just polyfluorinated chemicals. So being able to say per or polyfluoroalkyl substances is important in certain instances. So anyway, just a quick side note that you hear me say PFASs, and that is the original definition. And so it is this definition by Buck et al. That was adopted by Biomonitoring California, and they have a long history of looking at classes of chemicals for biomonitoring in the state. There's actually a paper from 2016, Croach et al., that looked at the possibility of or at the importance of taking a class approach to chemicals such as flame retardants and PFASs when investigating their presence in the California population. So, a lot of people, when they think about PFASs, it gets overwhelming because there's so many compounds and they are different. But I think it's important to think of them as 4 main subclasses. Pretty much all PFASs that were identified by Buck et al. Can be divided into one of these 4 subcategories. There's the perfluoroalkyl acids, or PFAS, which are the ones that we know most about, so that's your PFOA and PFOS. They're the terminal degradation products of most PFASs in the environment, as I'll talk more about that later. But these are the ones that we know most about. However, these are not the ones that are mainly used in consumer products. It's these PFA precursors that are the vast majority of PFASs, and they're the ones that tend to be used in most consumer products that we've looked at in my program. So some of these are pretty small molecules like fluorotelomers, but some of these can be polymers as well. So what we call side chain fluorinated polymers, which are a fluorotelomer based substance. They are polymers, but they're a big polymeric carbon chain with side chains that are fluorinated, and those side chains can cleave off, therefore producing PFAS in the environment. So this is the biggest category of PFASs as far as we know. And then there's these other 2 categories that are true polymers, meaning that the fluorine is embedded in the backbone. So there's fluoropolymers and perfluoropolyethers. And these are also used in consumer products, but I think the fluoropolymers tend to be in some of the more high-end applications, more high performance applications. You'll find them in industry or protective gear, or more high performance requirements. So it helps to think about these 4 different classes when you attempt to regulate PFASs. And unfortunately, most of the research that has been done to date has been focused on these perfluoroalkyl acids, and especially on the longer chain ones, so the ones that have 8 or more, 6 or more carbons for the sulfonates, 8 or more for the carboxylates. And this scale is logarithmic, so there's a lot more information on PFOA and PFOS than the other compounds, as David also mentioned. And that is basically a consequence of what we can measure and of where our interest has been. PFOA and PFOS have received initial attention because they were first discovered in environmental media and in people. And then we've expanded that to looking also at the shorter chains as we started seeing those in the environment. but there's only a few precursors that can be quantified right now using available analytical methods. Mainly, we only find these perfluoroalkyl acids in the environment because that's what we can measure. And so the vast majority of PFASs, we can detect their presence using non-targeted analysis. Some libraries have hundreds or maybe a couple thousand compounds, so it's possible to detect a lot of PFASs, like David showed that example from our work on food packaging, but we cannot quantify them. And that sets limitations in terms of regulating this class of compounds, right? If you have to do a risk assessment, but you can't actually measure the exposure, it's very, very difficult to do that. So how do we approach this in the Safer Consumer Products program? Well, when we get to this prioritization step, when we identify the priority products, our regulations ask us to take a narrative standard approach. So it's not a quantitative risk analysis. We do have to look at hazard and we do have to look at exposure, but only at the potential. And there's no quantitative risk assessment involved. So we have to demonstrate two key prioritization criteria: that there are potential exposures to a candidate chemical in the product, and that one or more of those exposures have the potential to contribute to or cause significant or widespread adverse impacts. And we tend to narrow the universe of consumer products that we look at. Every 3 years we publish a work plan. So these were the categories that we had in the work plan from 2018 to 2020. As I'm sure you can identify, PFASs are used in basically all of these categories. They're pretty much everywhere. So it was quite a challenge to prioritize what to look at first. So when we attempted to prioritize, we started with exposure, trying to figure out what are the biggest sources of exposure, or maybe the most concerning sources of exposure from the product categories that were in our work plan. And the exposure factors in the SEP regulations are broad. They include the market presence of the product, because the regulations are built in a way to allow us to take action when there is potential, but not necessarily definitive evidence. So they are inherently precautionary. So just the fact that a chemical is present in a product can be a concern. We also look at the occurrence or potential occurrence of exposures to the candidate chemical in the product. So not just that the chemical is present in the product, but how could exposures occur from that chemical in the product? And how frequently is that product present in households or workplaces in California? Is it something that's very common, or is it common for a subset of the population? Where is that product present? And importantly, we look at these potential exposures across the entire life cycle of the product. So we look at what happens during manufacturing, storage, transportation, use, end of life. So we really take a life cycle approach. The exposures do not have to happen during the use of the product. They could be at another stage of the life cycle. With PFASs, it was pretty easy to document potential exposure. I mean, as we know, they are ubiquitous, at least the ones that we can measure. They've been found in environmental media, indoors and outdoors, pretty much wherever scientists looked for them. They've been found in plants, animals, and in us humans, in our food, in our drinking water. This is just one of the maps from the California State Water Resources Control Board that looked at the presence of PFASs in multiple locations throughout the state. And yes, there are PFASs in a lot of different regions of California in the drinking water. And consumer products contribute to these exposures. They're obviously not the only source of PFASs in the environment, but they are a source. And for instance, carpets and rugs, which are one of the product categories that we looked at, they can lead to exposures for humans and biota through a multitude of routes. Of course, there's the direct exposure just by ingesting dust that contains PFASs that are coming out from that carpet, or inhaling the fluorotelomere alcohols that may be present in there. They can be volatile, and you can breathe them in. Dermal contact is not as well understood. It appears that there's not a lot of dermal exposure from the perfluoroalkyl acids, but that there may be dermal exposure for the fluorotelomere alcohols. So that is a potential as well. But there's a lot of exposures that happen kind of through the end of life of the carpet, or through cleaning the carpet. So, when you do your carpet cleaning, then that wastewater cleaning extract ends up to a wastewater treatment plant. The PFASs can end up either in the wastewater or in sludge. When the carpet reaches its end of life, it tends to be landfilled. We have a strong program in California trying to divert carpets from landfills, so there is some recycling going on as well, but still a lot of carpet makes it in landfills. And from there could be, again, emissions, either volatilized PFASs from landfills, or the leachate from landfills can also lead to contamination of groundwater, soil, and so on. So the biosolids from wastewater treatment plants, they're often reapplied to soil, and that basically brings PFASs back into this exposure cycle, right? We are not only exposed to them from the carpet itself, but those same PFASs can end up in our water, in our soil, and in our food. And so I really like this metaphor of the bathtub, that as long as you put PFASs in this bathtub, in the environment, as long as you don't turn the tap off, it will fill up and it will eventually overflow. So this is kind of a closed cycle with very little opportunities for these chemicals to escape the system, because they don't degrade, they just transform into other PFASs. And so carpets came to our attention because they are very widespread in our homes and workplaces. They're about half or more of the US flooring market. And back in 2017, when we started this research, we learned from the president of the Carpet and Rug Institute that most residential and commercial carpets are treated with PFASs. This has changed by now. I think a lot of carpet manufacturers have found replacements to PFASs, or are finding replacements to PFASs. So the market looks different now, but back in 2017, pretty much all carpets were treated with PFASs. And so that's where we started our work, looking at carpets and rugs. This is our technical document that outlines the rationale for regulating carpets and rugs as a priority product if they contain any member of the class of PFASs. And we initiated rulemaking on this last year in February, and the regulations are about to be finalized, and we expect them to become effective July 1st of this year. But because, if PFASs are removed from carpets during manufacturing, that may mean that the product is going to be cleaned more often. And so we also looked at the treatments that are being used aftermarket by consumers to treat converted textiles or leather products, such as carpets, furniture, clothing, shoes, leather bags, you name it, all these sorts of products. And we also issued a document proposing to regulate these treatments if they contain any member of the class of PFASs as a priority product. So we had a public comment period, and we expect to initiate rulemaking on this later this year. And lastly, we've also looked at plant fiber-based food packaging with PFASs. And again, we had a public comment period last summer, and we also expect to move forward with this and initiate rulemaking probably early next year. So we're now finalizing this document and incorporating all the feedback that we received. So these treatment products, they again can lead to exposures to humans and biota, either directly through using them, and in fact, there's a much greater risk of inhalation when you use these products. And again, through their end of life, either these cans or containers themselves when they're thrown away, or the products that are treated with these formulations, once they are reaching their end of life, they can lead to PFAS being released into the environment. So that's the rationale here for exposure was quite compelling. And the exposures and the chemicals that are used in here, they are not necessarily PFAS or the ones that we know most about, but they are precursors. And same with food packaging. And here it's a really interesting end of life fate, because the food packaging that is treated with PFAS tends to be what we consider compostable. It's plant fiber based packaging, molded fiber. So the idea with this packaging is to cut down on plastic waste and replace that non-biodegradable plastic that leads to microplastics and other environmental issues with something that can be composted and returned back into the carbon cycle. The problem, however, of course, is that PFAS are not compostable. And so that was a big concern for us and a reason why we chose to look at this food packaging category. But so that was exposure, right? The rationale in terms of potential for exposure. But when looking at adverse impact factors and the potential for adverse impacts, the SEP regulations allow us to look at hazard traits, and they distinguish between what they call exposure potential, toxicological, and environmental hazard traits. And aggregate effects, the different sources of exposure, or cumulative effects with other chemicals with the same or similar hazard traits or toxicological endpoints. We can also look at the physicochemical properties of a substance. If there isn't a lot known about their hazard traits, we can infer that based on physicochemical properties or environmental fate. And we can also look at the hazard traits and endpoints of the degradation, reaction, or metabolism products, as well as at structurally similar chemicals from where we can infer potential hazards. So this is quite a precautionary approach that's designed to give special consideration to the most vulnerable. And, in the case of PFAS, we now know quite a bit about these longer chain PFAS like PFOA and PFOS. We understand their potential for carcinogenicity, for cardiovascular toxicity, reproductive toxicity. We're now starting to understand their developmental toxicity potential. So there's a lot that we know about that, and their immunotoxicity. And similarly with the shorter chain PFAS that are used as replacements for the longer chain PFAS, we are starting to understand that they have some of the same hazard traits or even more. Some that haven't been documented for the longer chains have been documented for the shorter chains. So there's still potential for adverse impacts even from these newer formulations that are based on short chain compounds. There's also environmental hazard traits like phytotoxicity has been documented in lettuce, for instance. There's impairments to the developmental, reproductive, and survival abilities of wildlife that's been found in multiple species. These are just some examples here. And even though, there are all these toxicological reasons for being concerned about this class of compounds based on what we know so far, there isn't really one common toxicity or one common mode of action that the entire class shares. And so that really makes it difficult from a regulatory perspective to address this as a class of compounds. However, what they all have in common is what our regulations call an exposure potential hazard trait, and that's environmental persistence. We know that all PFAS are either persistent themselves or they degrade into other persistent PFAS. There's other exposure potential hazard traits that some member of this class show. For instance, mobility in the environment. PFAS, they all show that. The smaller fluorotelomeres are also very mobile. Bioaccumulation, that was shown for the longer chain PFAS in animals, in humans, but the shorter chain ones also accumulate in plants. So we're seeing some of these concerns for quite a few of these PFAS also. And lactational and transplacental transfer was also found, to my knowledge, for all the PFAS that were studied for these traits. So, they do have problems or characteristics that are problematic, but the one that unifies the class is persistence. All PFASs or their degradation, reaction, or metabolism products are highly persistent. These perfluoropolyethers, we found several papers that talk about the potential for forming PFAS when combusted, but they themselves also are persistent unless they're combusted, unless there's high temperatures that can convert them potentially into PFAS and other smaller fluorinated compounds. The PFA precursors, some of them are fairly persistent, but the ones that are not, they degrade to PFAS, and all of them eventually degrade to PFAS. And the fluoropolymers, like David mentioned, they are actually the main source of PFOA and long-chain PFAS contamination in the environment, historically speaking, because they are made using PFAS. And so now PFOA was replaced with Gen X and PFHXA and other short chains, but they're still a source of PFAS to the environment through their manufacturing, and they can contain these PFAS as impurities. And even though they don't degrade into PFAS in the environment, they are very persistent themselves. They can release PFAS during combustion, as a few studies have indicated or raised concerns about that. But the vast majority of PFASs are PFA precursors. So this is a chart from the OECD, the Organization for Economic Cooperation and Development, and they found that approximately 85% of the 4,700 PFASs that they cataloged are potential PFA precursors, either degrading into PFAS in the environment or being metabolized to PFAS inside organisms. And David also showed you this slide already, but I'll re-emphasize this because I think one of the crucial things to understand is that we know a lot about the PFAS, but most of the PFASs that have been used are precursors to PFAS. And what we know pretty much nothing about are these intermediate degradation products. Basically, the stuff that gets created as you convert from one of these precursors that are used in products to the PFA, that's the final degradation product. But from the very little information that we do have, we know that some of these intermediate degradation products may be more biopersistent and more toxic than the PFAS. So again, this is the example from the great work done by FDA scientists, a series of papers, Kabari et al. 2018 and 2020, that really showed the biopersistence of this 5,3-fluoroethyl carboxylic acid, or 5,3 acid, and then Rice et al. Demonstrated that it has higher toxicity than PFHXA. And so, we had this question earlier after David's section about whether it makes sense to regulate these as a class, or how can you regulate them as a class from a cleanup perspective. And I personally think that that's the only way that it makes sense to regulate them, because the PFAS that you understand the toxicity of, that we know the toxicity of, are just the tip of the iceberg. We need to regulate the precursors, because if we are exposed to precursors through our drinking water, that may actually be worse than being exposed to the PFAS, because the precursors can metabolize inside our bodies to degradation products that may be more toxic than the PFHXAs. So it may actually be worse to be exposed to these precursors than it is to be exposed to the PFHXAs, and we need to target those as well. So again, the only thing that they all have in common is persistence, and that's why several authors have really made a case for a piece-efficient approach. So Cousins et al., they had their paper in 2019, they had another one in 2020, making the case that if a chemical is highly persistent, its continuous release will lead to continuously increasing contamination and result in increasing probabilities of the occurrence of known and unknown effects. And this is key here, I think, because our understanding of the effect of these chemicals takes a while to develop. But if you're dealing with something that's so persistent, by the time you know all the effects, it's going to be too late and too expensive to really reverse that contamination. There were other authors as well that acknowledged persistence as the most important single criterion affecting chemical exposure and risk via the environment. That was McKay et al. In 2014. And we in California, we have this embedded in our code of regulations because of great work that was done by the Office of Environmental Health Hazard Assessment, or OEHA, who put together this list of hazard traits in Chapter 54 of the California Code of Regulations. So this quote is from their final statement of reasons for those regulations. I think there was some questions about whether persistence makes sense to list as a hazard trait. And they said that it does, because it is an inherent property of a chemical in the environment that results in increased exposure and in increased potential for health risks. So it can be identified as a hazard trait. And I think we're seeing more and more examples where it makes sense to regulate something because of its persistence alone. And PFASs are a great example of that. So we put together the rationale for our approach for why we have decided to take a piece-efficient approach to regulating PFASs as a class in consumer products in our recent paper that was published in Environmental Health Perspectives just last month. So if you haven't yet, I encourage you to take a look. And we really hope that this can be helpful for other regulators who are seeking to regulate PFASs in a comprehensive manner that is truly protective for public and environmental health. And we also have a couple short videos that go with that paper. So if you want some little fun alien trivia, you can take a look at that. So lastly, I want to conclude with, what's next? Well, we are listing these as priority products, but what comes next is going to be an alternatives analysis process. So we are asking manufacturers that are still using PFASs in those products to answer some quick key questions about whether the function is necessary, whether the chemical, the PFAS, is necessary. So coming back to that essential use, is the use essential? And if it is there a safer alternative? And what are the trade-offs? And we have an alternatives analysis guide that helps manufacturers answer those questions. And based on that, we take a regulatory response, which is really customized to each entity. So sometimes there may be no need for response, but sometimes we might ban the product, or if there are no safer alternatives, we could request funding into developing green chemistry solutions. So it's a whole range of regulatory responses that we could take. So with that, I'd like to thank you all for your attention. And if you'd like to stay connected, this is my contact information. And if you want to learn about our work, this is our e-list to which you can subscribe to get updates whenever we send out any kind of news about our work. So thank you again so much for having me here and for your attention.
Great. Well, thank you so much. And just a reminder to everybody that the slides, a PDF of the slides for both presentations today will be made available on the NMOA website. It takes a little while for everything to get posted, but I will send an email to everybody that attended today. So we do have a whole bunch of questions that have come in, and I'll just try to get through as many as we can. Can you expand upon PFAS impurities that you mentioned in slide 25? What's the nature of those, chemical nature, and what conditions under which they occur?
That's a great question. I mean, I wish I knew, but some of that information is proprietary and I don't have it. But generally speaking, when you make these PFASs, it's really impossible, from what I understand, it's virtually impossible to make a pure PFAS compound. There's always going to be some impurities in there. So especially for polymers, generally when you make a polymer, there's going to be monomer impurities in small amounts. So for fluoropolymers, there are PFA impurities because they're used as manufacturing aids during the manufacturing of those fluoropolymers. So we've seen several studies that look, for instance, at clothing that was treated with fluoropolymers or cycling fluorinated polymers, and they find PFAS. They were not intentionally added to that product, but they are impurities of the manufacturing process.
Okay. A couple questions are related to, does it look like California, now that you're looking as a class with consumer products, but how about coming up with numbers for drinking water or for soil cleanup that are more of a class approach? And what kind of metric would be used there?
Yeah, that's another great question. So I'm not that familiar with that work, but I know that OEHI is working on health goal levels and MCLs for several PFASs. It is a different regulatory process, and so I understand that there are challenges in trying to take a class approach to regulating PFASs in drinking water and in soil. So, we are talking with those colleagues, and they are trying to take as broad and as a precautionary an approach as they can. So, yeah, so far, I think one of the big challenges that David also mentioned is the fact that there are no accredited methods for doing like a total oxidizable precursor analysis or a total fluorine analysis. But from my understanding, those methods are in development. So once they have been developed and accredited, it may be possible to take a broader approach in those areas as well.
Okay, and this one can be for Simona and or David, but a few people have commented that some other chemicals have been sort of regulated as a class, including in sort of the cleanup world, like PCBs and dioxins and PAHs, polyaromatic hydrocarbons. So can you relate to sort of how that class approach developed for those chemicals and sort of how you could see things maybe going with PFAS approach? Where are there similarities and differences between the process of regulating as a class?
Yeah, I'll take a quick stab at it. I'm not a toxicologist, but my understanding is that these chemicals that have been regulated as a class before, they did have a common toxicity, and so that's where PFASs are different, because they have so many different chemistries, and we don't really understand their toxicity as well. There doesn't seem to be a common toxic mode of action for all of them. So I think those examples, they were more straightforward to regulate based on a toxicity point of view, unlike PFASs, where persistence is really the one thing that we know right now that connects the entire class, and that is of concern.
Yeah, but to add to that, at the same time, I think that does show that there is a precedent for at least considering the regulation of PFAS as a class. And really, this is most of issue and most relevant in terms of filling in data gaps across the class. And so I think that precedent is there. We mentioned a number of other examples in the PFAS as a class paper, the scientific basis for managing PFAS as a class paper also.
Okay. Can either or both of you speak to, a few people are concerned about carpets, so even though they've been phased out of use maybe here in the US, or PFOA and PFAS and hopefully all of them, but how about imported carpets and rugs and those sort of things? And then also, at the end of life, how can we actually destroy these things?
Yeah, great questions. So in California, our regulations impact imports as well. So we are considering anything that's manufactured, basically anything that's sold in California, whether it's manufactured in the US or overseas, it doesn't matter. So this will impact imports as well. And it's true that we don't know about what % of the imported rugs contain PFASs right now. We do know that carpets are mostly manufactured in the US. There aren't really a lot of imports of carpets, but the smaller area rugs, yes, there is a bigger imported market for rugs.
Destruction. Destroying. Oh, yeah, destruction.
So we're actually interesting. I actually worked with a team of students at UC Berkeley, and they have a course called Greener Solutions. where they work with the different industry groups or different stakeholders to address big green chemistry challenges. And so one of the challenges that they took on this year was the destruction of PFAS during carpet recycling. And there is no good way to do that right now, but they're continuing to work with a carpet recycler in California to develop a way to destroy, or at least remove and save for later destruction, PFAS from the recycling of carpet material. So yes, it's a very important point. It's much needed, and there is work being done to get to that.
Okay, so we're basically at the 3 o'clock time. There are a bunch more questions, and let's see, people are wondering whether we looked into effects about aquatic life and animals, if people have looked at whether autism and some of those things are affected in humans. Yeah, I don't know if any of you want to talk about either one of those branches of research.
Not sure about autism, but just very quickly, we have a pretty extensive list of papers that we reviewed and an appendix with a lot of the tox effects. Not everything, but a lot of them, and you can find that in the reports that I linked in my presentation. So once you get the slides, you can go and see the reports and the information in there.
Great. Well, like I said, the slides will be available. They have the links to websites in the slides, and also I think the contact information for each of the presenters today. So I think it's a good time to end. Thank you so much to Simona and to Dave for your time and your presentations today, and to everybody else that stuck with us here on the webinar, and I hope you will join us again. So I hope everybody has a nice rest of your afternoon, and thank you again to Simona and Dave.
Thank you.
Thanks a lot.
I'm going to sign off. So thanks, everybody. Bye-bye.